Irrational numbers. The numbers which are not rational. The opposite of rational is irrational. So any number which is not a rational number is an irrational number. So any number which cannot be expressed in the form p by q, with p and q being integers and q not equal to 0, is an irrational number. I think you all get it now what an irrational number is. Irrational numbers is denoted by all real numbers except q is how we denote the set of irrational numbers, and it is anything which is expressed in the form p by q such that q not equal to 0 minus p by q such that p, q are integers and q not equal to 0 is how we understand the irrational numbers. Let's try to see more better examples to understand what an irrational number is. Before we try to identify the irrational number, the most easiest concept is identify for the given number to be a rational or not a rational number. If the number is a rational number, it is not irrational. If the number is not a rational number, then it must be an irrational number, is how we understand. Let's start with an example problem. Is this an irrational number? Is the question out here. So root 5 over 9, let's test for this being a rational or an irrational number. For example, root 5 over 9 can be differentiated with the numerator being p and the denominator being q. Now clearly my p is root 5 and my q is 9. So let me put this to the two tests of the rational numbers. So with the test number 1, I clearly identify that q equal to 9 belongs to z, but p equal to root 5 cannot be an integer. Therefore, my p equal to root 5 does not belong to z. Therefore, this number root 5 over 9 fails the first test for a rational number. And therefore, root 5 over 9 does not belong to q. It is not a rational number. So this is not a rational number, so it is an irrational number. Therefore, root 5 9 over 9 is an irrational number denoted by all real numbers except q r minus q, is how we justify an irrational number through the concept of q. Here being this is not a rational number, so obviously it must be an irrational number. Now let's try to take more examples to understand the irrational number more better. So let's take an example problem here which says with the question, is root 5 an irrational number? Or I take root 9 because I just want to have an example which is not an irrational number. So my question here is root 9 an irrational number? So here with this example, I clearly try to simplify this to a more simplified form where root 9 can be expressed as 3, which in turn can be expressed in the form p by q because I need to put through test number 1 and test number 2. So this can be expressed as 3 over 1 where my numerator is p and my denominator is q. Therefore, I have my p which is 3 and I have my q which is 1. And clearly these two pass through the test number 1 which belongs to z. P and q belong to z and it passes through test number 1. And test number 2, because q equal to 1 can never be equal to 0, therefore this passes through both the tests of the rational number. Therefore, I clearly understand root 9 is a rational number because root 9 indirectly expressed as 3 passes through the two tests. It is a rational number, and therefore root 9 cannot be an irrational number. A number which is rational can never be rational, and a number which is irrational can never be rational, and therefore root 9 being a rational number cannot be an irrational number. Is how we justify the irrationality of a number based on its rationality. To be continued with the examples, this session deals with the exceptional irrational numbers which we identify in the branch of mathematics. So let's see what these exceptional irrational numbers are out here. For example, I take the most popular mathematical symbol, which is pi. We all know that pi has a specific value, that is 3.14, and it continues forever without ending. Now this approximately we take as 22 by 7. So pi is approximately 22 over 7, but let's see if this is a rational or an irrational number. When I go with pi being 22 by 7, I clearly see that its p is 22 and its q is 7, so that my p is 22 in the numerator and my q is 7 in the denominator, and both belong to z. Therefore, this number pi, which is 22 over 7, passes through test number 1. And similarly, my denominator, which is q, is not equal to 0, is the test number 2, which the number 22 over 7 passes out in rationality. But when you see this clearly, because of the two tests, 22 by 7 is a rational number. Therefore, I need to assume that pi is a rational number. But this is an exceptional irrational number. Though it passes through the test of 22 over 7 being a q, cannot make pi as an irrational number. Cannot make it as a rational number, because pi is a mysterious number which has its value unending. Because we cannot predict, we only take the approximation of pi to 22 over 7, but not exactly equal to 22 over 7, and therefore this is not exactly a rational number. It is an exceptional irrational number. But pi is an exceptional irrational number. R minus q is how we identify the specific numbers in mathematics which are not accepted in irrational numbers. So it's an exceptional irrational number, pi. There's one more example which we can take, which is E. E is approximately 2.71, which is also an exceptional irrational number. So in the branch of mathematics, E and pi are exceptional irrational numbers, is how we identify in the branch of mathematics. Let's take one more example of an irrational number, which is very essential to understand the set of irrational numbers as compared to the rational numbers in the branch of mathematics. Non-terminating decimals. Let's justify for this to be a rational or an irrational number. What is a non-terminating decimal? A decimal which never stops, but it goes on repeating and repeating, is how we understand a non-terminating or a non-stopping decimal. For example, if I take a decimal in the form this seems to be never ending. As I form a sequence, this repeats never ending on and on till infinity. So such a decimal in the branch of mathematics is called a non-terminating or a non-stopping, never stopping decimal out here. So let's see if this can be a rational or an irrational number. To start with, the rational number with the two tests as we have already discussed in the session. Now, for the test, this should be expressed in the form P by Q, but because it never ends out on the right, this cannot be expressed in the form P by Q. X cannot be expressed in P by Q form as the decimals never end. As the decimal part never ends, and therefore this, because it cannot be expressed in P by Q form, therefore X cannot be a rational number. In order that it should be a rational number, the first essential thing is that it should be expressed in the form P by Q, with test 1 and test 2 being followed with that. But because it cannot be expressed in P by Q form, X cannot be a rational number. Therefore, any terminating decimal can never be a rational number. A terminating decimal is always an irrational number, is how we identify the property out here. So the outcome is that the terminating decimal belongs to R minus Q, is how I understand the property of the terminating decimal being an irrational number. Always can never be a rational number. Now the last set of numbers in the field of mathematics in here is real numbers. Starting with natural numbers, we proceeded with natural numbers to whole numbers to integers, integers to rational numbers to irrational numbers, and finally from irrational numbers to the real numbers. So real numbers are generally denoted by R, and it has the same definition as that of rational numbers, with only the test number 2 absent out here, with test number 1 absent out here. So for example, I have this R denoted by capital R. My real numbers is defined as P over Q such that Q not equal to 0. So I clearly understand that in the absence of test 1, I don't have the condition for the numerator and denominator to be integers, provided the denominator should never be equal to 0 in any of the numbers in the number system, because 1 by 0 is infinity, undefined. So real numbers is this, P by Q such that Q not equal to 0, irrespective of the condition for P and Q being any integer or a non-integer. For example, I have a question which says, is root 3 over root 7 a real number? So let's see if this is a real number. Root 3 over root 7, which can be written in the form P by Q, clearly states that Q is equal to root 7 can never be equal to 0, because root 7 is a non-zero irrational number. Therefore, Q not equal to 0 is the test, which is the only test which needs to be passed for a number being a real number. Now this test is passed, therefore root 3 over root 7 is a real number. But this cannot be a rational number because P and Q are not integers. Root 3 over root 7 is not a rational number, is how we understand the difference between a real number and a rational number. A rational number, we have the numerator and denominator to be integers, but in real number, the only condition being denominator should never be equal to 0. So root 3 over root 7 is a real number, but root 3 over root 7 is not a rational number, is how we understand the concept. Instead, root 3 over root 7 is an irrational number and a real number, but not a rational number. Now let's take another example to see if the given number in the question is a real number or not a real number. For example, I have the question, is 7 by 0 a real number? Is the question out here. So let's pick the given number 7 over 0, as clearly I see that it is in the form P by Q, with Q being tested for the real number. Now clearly I have Q equal to 0, which fails with the test that Q should not be equal to 0. Therefore, this number which fails the test of a real number clearly states that 7 over 0 can never be a real number, is how we understand the real number is all sets of numbers with only the exception to those numbers whose denominator is 0, is how we understand the set of real numbers. Now let's see the relation of 0 in the denominator connected with R, Q, R minus Q, Z, W and N. So as we have discussed in each of the examples, we have identified a very important note that for any number where the denominator is 0 can never be a real number, can never be an irrational number, can never be a rational number, can never be an integer, or can never be a whole number, or can never be an integer. So the branch of mathematics does not accept a number with denominator 0 in any of its number system. It's an exception for the number system itself, simply because 1 by 0 is infinity, and which is undefined, is the reason why this is an exception to the number system. Now that we have discussed about the different types of set of numbers in the number system, let's try to compare all of the numbers, the set of real numbers, set of irrational numbers, set of rational numbers, set of integers, set of whole numbers and set of natural numbers combined together, and the relation of each to the other. Now this is more important in understanding through the Venn diagrammatic representation. So let's take the Venn diagrammatic representation to understand each of the sets. Now we have the set of real numbers denoted by R, and I have the set of rational numbers denoted by Q, and I have the set of integers denoted by Z, and I have set of whole numbers denoted by W, and set of natural numbers denoted by N, is how we denote through the circular or the Venn diagrammatic representation. So here I clearly understand that the bigger circle or the bigger set is R, so this is the mother of all the sets. So real numbers is what through which all the numbers come out, and the least set is natural numbers. So this makes me clearly understand that all rational numbers which are inside the circle of the real numbers makes me clearly understand that all rational numbers are part of real numbers. So every irrational number is a real number. Every integer is a rational number, and every integer is a real number. Every whole number is an integer, every whole number is a rational number, or every whole number is a real number. Similarly, every natural number is a whole number, every natural number is a real number, every natural number is a rational number. But if you go the other way, every integer is not a natural number, because z is not inside n, but n is inside z. So every natural number is an integer, but every integer is not a natural number. Similarly, every rational number is a real number, but every real number is not a rational number, because R is outside Q and Q is inside R, is how we can easily analyze the properties using the simple diagrammatic representation N, W, Z, Q and R, which makes us understand whether the number is a subset of each of it. The other way of representing this Venn diagrammatic or the circular representation is that N is part of W and W is part of Z and Z is part of Q and Q is part of R, is how we understand the relation between each of them. And more importantly, this region between the rational number and the real numbers is irrational numbers, which is represented here. So this region represents all the irrational numbers which lie between the rational and real in this region of, is how we understand the different set of numbers in the branch of mathematics which are related, interlinked to each other through this Venn diagrammatic representation. Now that we have discussed about different types of number systems in the branch of mathematics, the real numbers, the rational numbers, irrational, integers, whole numbers and natural numbers, now let's see how we can represent the irrational numbers which are not the exact numbers on the number line, the real number line. Let's recap the irrational numbers which we have discussed in the previous sessions. Irrational numbers, as we have discussed, are the elements which are written in the form R minus Q. So all numbers which are not rational or which cannot be expressed in the form P by Q, failing both the tests, PQ belonging to Z and Q not equal to 0, is how we define irrational numbers. So let's see how these irrational numbers can be exactly located on the number line through the exact distances. For example, I take the irrational number root 2, which is clearly an irrational number. Now, when I convert this into the decimal representation, we know that root 2 is approximately 1.414 and dash dash. Now, because this is not an exact number, even in its decimal place, we will try to use some geometrical construction methods to represent root 2 on the number line through the exact distance. Let's see how we can do this. Before we just try to construct root 2 on a number line, let's try to recap with some geometrical constructions which are useful in construction of root 2 on the number line. For example, I take a square of side 1 unit. So here I have a square of side 1 unit with all sides being equal with 1 unit on each side. Now here I try to extend the diagonal from one corner to the other corner. So we know that this diagonal forms the hypotenuse for one of the right angled triangle taken on either side of the diagonal for the square. Now this being a right angled triangle, let me say this is A, B and C. So ABC forms a right angled triangle, right angled at B, with AB equals 1 unit and BC equals 1 unit. Therefore, by using Pythagoras theorem, I have AB square plus BC square equals AC square, and which on further representation of the given values gives me 1 square plus 1 square is equals AC square using Pythagoras theorem. Now when I further simplify this, I get this to be AC square equals 1 square which is 1 and 1 square which is 1, when on further adding up gives me AC square equals 2. That implies my length AC, which is the diagonal of the square, equals root of 2 is how I get the root 2 out of 1 unit of the square. So this dimension of the diagonal being root 2 is what we utilize in representation of root 2, which is an irrational number on the number line. So let's see how we can just take this further into geometrically constructing root 2 on the number line. Let me take the number line before we construct root 2 on the number line, or representation of root 2 on the number line. So here is the real number line, which extends from minus infinity to plus infinity, with all the points on this line being the numbers of the real numbers, or the real numbers of the number system. So here I have the real number line, which is represented through the line and called the number line, and here I have exactly in between the neutral 0, from where on the right side you have all positive values, on the left side it's all negative values. So let me just proceed with the right side of the values, which is 0, 1, and next comes 2 and 3, and so on and so forth to infinity on the right. Similarly, on the left, I have negative 1, negative 2, negative 3, and etc. onto the negative side of the infinity. Now, let's try to see how we can construct root 2 on this number line, using the previous discussion of the square, which gives me with the dimension of 1 unit, and its diagonal, which gives me the distance of root 2. So let's see how this can be transferred into the number line to get the same root 2 on the number line. So in order to do that, I need to have this diagonal placed on this number line, which is possible by constructing a square of 1 unit. So here is 1 unit. So I construct a square of 1 unit on each side in this form. So once I construct a square of 1 unit starting from 0 to 1, that is a square being built on the number line, I try to join this diagonal from one end to the other end. Let me just mark this as A. Now OA is the diagonal for this square, which we know indirectly is root 2. Therefore, I just transform this dimension into root 2 out here. So I get to be OA equals root 2 units, using the concept of the square, which we have already discussed in the session. Now with this root 2 units, now I take a compass and just point it at O and put the compass at A and just draw an arc. So when an arc is cut, I just get an arc which cuts the number line, indirectly stating that this forms a circle with same radius. Therefore, the radius of root 2 units made by the compass is nothing but the radius of the same root 2 units as made by the compass on the number line, and thus we get the distance root 2 out of the square diagonal in this manner. So when we would like to construct root 2 on the number line, we try to first construct a square of 1 unit on the number line from 0 to 1 unit, and then take its diagonal, measure the diagonal with the compass, then draw an arc such that the arc cuts the number line. And the point where the arc cuts the number line, I denote it with B, and OB is root 2 for sure, because the radius is the same for any part of the circle from its fixed center. Therefore, my OB as constructed from the arc is also root 2 units, because it is the same radii, the same radius concept, and therefore my distance on the number line from O to B is what is the distance, which is an irrational number, root 2, which can be represented on the number line in this manner of constructing through the geometrical square diagonal. Next, let's see how to represent the irrational number root 3 on the number line. Of course, root 3 has the value which is 1.732 and so on and so forth in its decimal representation. So this value root 3 an irrational number root 3, I would like to represent on the number line, just like root 2, how it can be represented on the number line. So let's see what geometrical concept can be used in case of root 3 to construct on the real number line. So here I have, say for example, I take a right angle triangle and I have this to be an isosceles right angle triangle, 1 unit and 1 unit, and therefore of course it's an isosceles. So these two sides being equal, it is an isosceles right angle triangle such that the two sides are 1 unit each. Then obviously by using Pythagoras theorem, we know that the hypotenuse is root 2 units, as we have seen in the previous session of the diagonal of a square. So this being root 2 units, let's see how we can develop root 3 using this root 2. Imagine I take the point OAB and I try to take the point O and I construct a line perpendicular to OA and passing through A. That is, I draw a line through A perpendicular to OA, the side OA of the triangle OAB. So here I construct exactly with the distance being 1 unit. So this is exactly same as this of 1 unit. So here I mark this to be C. So C is the point which is exactly 1 unit from A and which is perpendicular to the side, the hypotenuse OA of the right angle triangle. So now I have the side CA which is 1 unit and I have the side OA which is root 2 units, as we can clearly see through the diagram. Now with this, let me join C to O. Say I just join C to O out here. Now let's try to calculate the dimensions of the side OC which is joined for this triangle ACO. Now let me just focus on triangle OAC and let's see what we witness from this triangle OAC. As we can see the triangle OAC, we see that AC is 1 unit and OA clearly is root 2 units, is what we have from these two dimensions. And clearly this being 90 degrees, it's a right angle triangle, and therefore we have the Pythagoras theorem which comes into existence. Triangle OAC is a right angled triangle, and therefore this being a right angled triangle, we are going to focus on the Pythagoras theorem. So let's see what happens with Pythagoras theorem applied out here. So we know that in right angle triangle OAC, the hypotenuse OC square is sum of squares of other two sides, that is OA square plus AC square. And then when I further substitute the values, I get this to be OC square is equal to OA, which is root 2 whole square, and AC, which is 1 whole square, which on further simplification gives root 2 whole square. We know that root x into root x, which is root x whole square, is x, because the root and the square both get cancelled, and therefore I get x. Similarly, root 2 times root 2, which is root 2 square, is 2, and 1 square, which is 1, which is finally 2 plus 1, and that is equal to 3. Now in this case, when I further simplify this, I get this to be OC square is 3. That implies my dimension OC is square root of 3. When the square comes out here, it comes out as root of 3 units. So this is how I get the dimension of OC. Constructing or locating root 3 on number line, we use this geometrical concept of the triangle, and finally we get the distance OC, which is root 3 units. And this is how we locate this on the number line, is how we just understand geometrical construction of root 3 on the number line using the right angle triangle and most importantly the Pythagoras theorem of the right angle triangle. Now let's take the real number line and construct root 3 or locate root 3 on that real number line. So I have the real number line out here, which extends itself from minus infinity to plus infinity, is how this extends. And here we have the neutral 0 through which on the right hand side they extend up to 1, 2, 3, 4 and so on and so forth, and the left hand side has minus 1, minus 2, minus 3, etc. Now on this real number line I take a right angle triangle, as we have seen that root 3 was constructed through an isosceles right angle triangle, 1, 1, root 2, 1, and this finally gives me root 3. So I'm going to use this concept of the geometrical triangles on the number line, and finally this distance is taken as the radius arc, and when you draw through the compass it cuts the number line exactly at root 3 units, is the concept which we are going to use in here. So when I take isosceles right angle triangle from 0 to 1 with 1 unit each, I get this to be 1 and 1, and this extends in the diagonal with this to be root 2. And finally from here I take a compass, I drop the perpendicular, and then I just get this to be exactly 1 unit. I measure the length 1 unit and cut an arc, and then I get a triangle with the dimension of root 3. So here is, say for example, OA with length root 3 units. So I have the length OA, which is root 3 units, as constructed through the Pythagoras theorem and discussed in the previous session. I take the compass, put the center at O, and just draw an arc from A, and I get this to be an arc which extends out here, and therefore I get the radius root 3, which is also the radius out here on the number line. So this distance is root 3 units, which cuts, say, at the point B. So my OB on the number line is root 3 units, which I construct on the number line. On real number line, my length OB is root 3 units, is how I locate the irrational numbers through the geometrical processes on the number line. Rational numbers on real number line. Now that we have seen the process of locating root 2, root 3 on the number line, what about root 5, root 6, root 7, root 8, or other square roots which can be represented on the number line? Is it that only root 2 and root 3 are the only numbers which can be represented on the number line? Or are there every irrational number which can be represented on the real number line, is the biggest question out here. So let's see, investigating on further irrational numbers, let's see a consecutive pattern or a process which can be identified on construction of the irrational numbers using the geometrical concepts. So here my session today is about locating square root of n on the number line, of course the real number line. So let's start with 1. Let me just take O and A, and here I have A, and this is 1 unit, and then I have this to be also 1 unit with 90 degrees. Then from here, when I take this to be B, I have OB clearly, which is root 2 from Pythagoras theorem. So this is 1 unit and this is 1 unit. So this is root 2. Now using root 2 and the distance of 1 unit, I get this to be again a Pythagoras theorem, which gives me root 3. Again, taking this as C, OC is root 3, and next I construct a perpendicular from at C and at a distance of 1 unit, then what I join here will be root 4. Let's see how it comes. So when this distance OC is root 3 and say my distance from D to C is 1 unit, and then this forms a right angle triangle ODC. In triangle ODC, which is a right angle triangle, I have the Pythagoras theorem which says OD square is equal to OC square plus CD square. Now we know that OD square is what we need to find, with OC being root 2. So I have this to be root 3 square plus CD square, which is 1 square. Now this root 3 square is 3 and 1 square is 1. With square root and root gets cancelled with the square. I get this to be 4. Then I get my OD, which is root 4. Of course, root 4 is 2. So my distance OD is root 4, through which I again proceed in the same process, so that I take from D a perpendicular of 1 unit which cuts D exactly 90 degrees. And here, this being 1 unit, let me mark this with E and then join OE. Let me again take triangle ODE. In triangle ODE, which is a right angle triangle, right angled at D, I have again the Pythagoras theorem, which plays a vital role. So using the Pythagoras theorem, the hypotenuse OE square will be equal to sum of squares of other two sides, which is OD square plus DE square. Now I have my OD, which is calculated as root 4 or 2. So OD, which is root 4 or 2 square, plus DE, which is 1 of square, gives me 4 plus 1, which is 5. Therefore, OE square is 5, implies my length OE is root 5. This is how I identify that as I construct the 1 unit perpendicular length on through the different sides of the polygon, I get the different distances from O, which are nothing but the roots in consecutive integers or roots in consecutive natural numbers. So I have root 1. This can also be taken as root 1. This as root 2, root 3, root 4, and then finally this comes out to be root 5. So this distance OE is root 5 units. So in order to construct the root 6, we again take 1 unit perpendicular from E exactly with a length of 1 unit, join the dimension, we get root 6, root 7, root 8, root 9. So one important thing what we note is, in order to find root 5, we need the length root 4. In order to find the length root 4, we need the length root 3. In order to find length root 3, we need the length root 2. In order to find the length root 2, we need the length 1. So it all starts from 1 unit. Therefore, in order to find the length root n, we need the length root n minus 1, 1 short of unit. So therefore, I come with the learning outcome. In order to find the length root n, I need to find the length this first. So in order that I find the length root 5, I need to first find the length root 4 before I find the length root 5, or locate root 5 on the real number line. So its consecutive or its preceding root number should be identified before we locate the next coming natural number under the root. So in order to find the length root n, I need to find the length root n minus 1 first, is what I make the learning outcome out in this session. So finally, root n for all n belonging to z plus can be represented on the real number line. If here being n belongs to z plus is how we identify the location of irrational number on the real number line. So the square root spiral, which we call this, is the useful tool in identifying the irrational number on the real number line. So number line can have the rational numbers being located using this square spiral.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.